All right, so today we're going to be discussing a topic from section 11.11, which is related to Taylor polynomials. So, just to get us back on the page here to remind ourselves of things that we've seen that if you have a power series, so this is a function which is itself a series that essentially takes the form of an infinite degree polynomial. You can, from a power series, this power series happens to be centered at x equals a, you can correspondingly get a grip on the coefficients that are associated with the term of a particular degree by looking at the derivative of that function evaluated at a and divided by the appropriate factorial. So in particular, if you want the coefficient that is in front of the degree 5 term, you would take the fifth derivative of your function, evaluate at a, and divide by 5 factorial. This fact is frequently referred to as Taylor's theorem, and what this allows you to do is to cook up a Taylor series associated with a given function. So, if you are given a function that is differentiable, a function for which you can compute derivatives, well then we have the ability to develop the associated Taylor series using Taylor's theorem. And how do we do this? I guess we do this in the manner that we sort of have worked through to this point, which is fairly algorithmic. It's a process, but if we sort of trust the process and take it for what it is, we can cook ourselves up the Taylor series. So how do we do this? We look at the function and its derivatives progressively all the way down. We subsequently then take the formulas for the derivatives that we get and we evaluate them at a. A is the center of the series. So as in the example above here, the center of the series is at a. And then what do we do after we evaluate the derivatives at a? Well, then we just simply divide by n factorial, and what pops out are precisely the coefficients that go into your corresponding Taylor series. And if you want to expand out this Taylor series just to see it in sort of full articulate form, you've got the 0 degree coefficient by itself, the 1 degree coefficient times a 1 degree polynomial, the 2 degree coefficient times a 2 degree polynomial, and so on and so forth. So C3 would be associated with x minus a to the third, C10 would be associated with x minus a to the 10th. And this dot dot means that this goes on forever. In fact, this sum here associated with the Taylor series is from n equals 0 to infinity. Now, having said all of this, you might say, well, okay, great, I know this. I was watching the videos last week and saw what a Taylor series is. Isn't the topic of today Taylor polynomials? Yes, it is. So then the question becomes, what is a Taylor polynomial, right? And the simplest way to discuss this is that a Taylor polynomial is just a truncated Taylor series. So when it comes to a Taylor series goes on forever. Now you know that polynomials are not of infinite degree. Polynomials eventually stop. They eventually have a highest degree term. And so what we're going to be talking about are Taylor polynomials, and that is essentially looking at your Taylor series and cutting it off eventually. So for example, if I would disregard this dot 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 and instead focus strictly on the terms of degree 0, degree 1, and degree 2, this would be an example of a degree 2 Taylor polynomial. So it's not the whole series, just the part of the series up to a particular degree, which in some sense is actually a simpler task than computing a Taylor series. Because to compute a Taylor series, you've got to compute all of the terms up to whatever degree would be possible out to infinity, whereas for a Taylor polynomial, you just go up to a particular degree and then stop. So in some sense, the truncated process is actually a simpler process. That being said, let's dive into an example so we can see this in action. So find the degree 3 Taylor polynomial for f of x equals square root x centered at a equals 9. So a couple things to note. First, we're only going up to degree 3 Taylor polynomial. So as we set up our chart only goes down to the third derivative, because to get the degree 3 coefficient, we have to go down to the third derivative. Everything beyond that n equals 3 derivative is senseless to compute, given that we're only focusing on the degree 3 Taylor polynomial. Second, this function is differentiable. You could take its derivative because, in fact, viewing this as not in square root notation, but in exponential notation, we could write this as x to the 1/2 and just apply the power rule repeatedly to get subsequent derivatives. So because this function is differentiable, it has a chance of applying Taylor's theorem to it. Note, the center here is going to be at a equals 9. So what does that mean? That means that each individual polynomial term of particular degree is of the form x minus 9 to whatever power. So the degree 1 term is going to be just x minus 9, the degree 2 term x minus 9 squared, degree 3 term x minus 9 cubed, and so on. Well, actually, in general, we would go and so on, but in this case, since all we're focused on is the degree 3 polynomial, when we get here, this is actually a period. This is the truncated Taylor series that has been truncated at the degree 3 term. So once we figure out these 4 constants, we've got it. And how do you figure out those constants? You go through the classic algorithm. So you take the original function, compute its derivative, just simply application of the power rule, compute another derivative, yet another application of the power rule, compute another derivative, yet another application of the power rule. Here we don't have to figure out what the general form of the derivative looks like. We just have to get what the actual functions are associated. Now, next column, what do we do with our derivatives? We evaluate them at the center. Here, we are centering our polynomial at a equals 9, so we're going to plug in 9 where we see x, and we're going to work through the computation. And so in each of these cases, we're just plugging in, like here, 9 to the 1/2 power, that's the square root of 9. 9 to the negative 1/2 power is going to put a 3 downstairs and give us 1/6, and so on. So we just compute, sort of plug and chug, right? I mean, you could throw this in your calculator, worst case scenario, to compute these values. But now, once you plug in a equals 9, you are not done yet, although you're close. You subsequently have to divide by n factorial. So in this case, we've divided by 0 factorial, which is 1. Next, we divide by 1 factorial, which is also 1. Here we divide by 2 factorial, which is 2. So note the denominator is twice the size it was, because division by 2 is like multiplication by 2 in the denominator. And this next guy is going to be divided by 3 factorial, which 3 factorial is 6, right? 3 times 2 times 1. So note the denominator is 6 times the size, because division by 6 is like multiplication by 6 in the denominator. But now, what pops out in this last column is the coefficient for each degree term that we need from 0 to 3. So our constant coefficient is 3. The coefficient in front of our degree 1 term is that 1/6. The coefficient in front of our degree 2 term is that minus 1 over 216. And the coefficient in front of our degree 3 term is 1 over 3,888, as it turned out. And the long story short is this polynomial, note it's a degree 3 polynomial, is the degree 3 Taylor polynomial associated with our function. What does that mean? Well, based on our analysis here through our algorithm of following Taylor's theorem, this function will agree with our function f of x at 3 derivatives at a equals 9. So at the point x equals 9, this function agrees with our function, both in terms of its initial function value and in terms of its degree 1 first derivative, and in terms of its second derivative, and in terms of its third derivative. So this function has the same value as our function. This function has the same slope as our function. This function has the same concavity as our function. This function has the same whatever the hell the third derivative describes in terms of the shape of the graph of the function. It has that same character with respect to third derivative. So, and you can think about this. If you had the same function value, if you had the same slope, if you had the same concavity, if you even had more derivatives in common than just the first 2 derivatives, boy, you should be doing a decent job at describing what's going on with this function. And indeed, that's the case. Now, is this degree 3 Taylor polynomial going to give you exactly the function values back? No, but near a equals 9, it's going to give you a pretty damn good idea of what's going on. And so if I may, actually, to come down here to the sort of the final question and answer for this portion of video, what is a Taylor polynomial good for? The answer is approximating the function. Because like taking the square root of a number that's not exactly 9 but near 9 is actually pretty difficult to do, right? Like what's the square root of 10? I mean, if I asked you to give me that value precisely to like 5 or 4, let's say 4 decimal places. Give me the square root of 10 to 4 decimal places. That's not easy to do. Like, that's going to take a lot of checking, and you're going to have to check a lot of decimal multiplication to see if you've got something that's appropriately close. It sounds messy, frankly. But what the Taylor polynomial allows you to do is get a function, which is relatively easy to compute. Think about this. If you plug in 10 where x is, you're just going to get 1 and 1 squared and 1 cubed, which is actually not that hard to work with, because actually doing polynomial computations is really not that bad. And, the polynomial computation at x equals 10 is pretty near the center, and this function agrees with our function at 3 derivatives deep, I guess, at the point x equals 9. X equals 10 is pretty close to x equals 9. Hey, this function should give us a pretty good idea of what our actual function would evaluate to. So a Taylor polynomial doesn't give you exactly the value of f of x. And for sure, there's no guarantee that it's going to give you exactly the value of x when you're far away from a. I mean, if you want to know what the square root of 110 is, don't center your Taylor polynomial at a equals 9. Center your Taylor polynomial at a equals 100. But if you want to know what the square root of 10 is, then centering your Taylor polynomial at a equals 9, which wasn't really that hard of a value to work, right? Because with the square root 9 is no big deal. Well, then we're going to get a pretty good approximation near x equals 9. So the Taylor polynomial is a way to approximate a function. It doesn't give you exactly the value of the function, but near the center, it's going to give you a pretty damn good estimate. And so to take this square root 10 idea and extend it to our particular case, well, square root 10 would be approximately equal to what our Taylor polynomial would evaluate to at 10, because 10 is pretty close to 9. Well, again, if we plug in 10 here, we just get 1 and 1 squared and 1 to the third for those polynomial factors. And so ultimately from the Taylor polynomial, we get 3 plus a sixth minus 1 over 216 plus 1 over 3,888. And if you hammer this out, you get 3.162294, which is, you know, whatever. It's the decimal expansion of this number that you would get whenever you'd add up all those fractions. And then you say, well, so what? How do I know that that's close to square root 10? Well, I also happen to have computed square root 10, and that comes out to be 3.1622776. So, I mean, hey, we're pretty damn close, right? I mean, we got it within 4 decimal places. And it really wasn't actually that hard to produce this this polynomial. And now you say, well, wait a second. I mean, I could have figured that out within 4 decimal places, maybe in the same amount of time. Perhaps you could. But now, what if I subsequently asked you to find the square root of 9.5? You're going to go straight back to the drawing board. Whereas since we've got the degree 3 Taylor polynomial, if we want to know the square root of 9.5, we just plug and chug. You want to know the square root of 8.5 approximately? Throw 8.5 in the formula, and you could get that. The square root of 8, similar story. So I guess the long story short on the Taylor polynomial is it provides a simple computation to potentially make swift work of what would otherwise be a cumbersome computation, not to give you the exact value, but to give you an approximate value. So as long as you're trying to just simply approximate your function and get near the center, then the Taylor polynomial is a wonderful tool in order to give you such data.